Keiner? Wir legen los, okay?
Ja, wir können loslegen. Ja.
Einen schönen guten Nachmittag zusammen. Herzlich willkommen zum nächsten Vortrag im Rahmen dieses Seminars, Seminar für erneuerbare Energien. Den einleitenden Witz, ja, kennen Sie alle, treffen sich zwei Päpste. Das funktioniert nicht so wirklich normalerweise. Wir haben es jetzt geschafft, zwei Päpste hier gleichermaßen gleichzeitig auf die Bühne zu bringen. Einmal den Kollegen Michael Kauffeld aus MMT, der hier auch das Institut für Kälte, Klima, Umwelttechnik leitet, ja, der, wenn man so will, der Papst für Kältetechnik hier in Deutschland. Und wir haben den internationalen Papst dabei, den Wärmepumpenpapst, der eben aufgrund des des Wärmepumpensymposiums, was morgen an der Hochschule stattfindet, auch hier ist. So it's a special pleasure for me to welcome Professor Björn Palm from the Royal Institute of Technology in Stockholm, if I'm right. And I just have the pleasure to hand over to you. Maybe you introduce yourself a little bit, and we're looking forward for your presentation.
Thank you. Thank you very much. So, good afternoon, everyone. It's a pleasure to be here and to be able to talk to you today about a very important subject, I think, importance of heat pumps in the future energy systems. And I understand that many of you are studying electrical engineering, so I think you will like what I'm saying. We have divided now the presentation here, so I will give sort of an introduction why heat pumps are important, and then Michael will talk more about how a heat pump works. So my presentation will be rather easy to understand, I think, for everyone. And just to tell you who I am, I come from the Royal Institute of Technology in Stockholm, and we at the Department of Energy Technology. And we have a group called Applied Thermodynamics and Refrigeration. So we have been working on heat pumps and refrigeration equipment for almost 100 years. Yeah, I think that is enough as a background. Now let's see. Yeah, we have the right slides here. So just to give you an idea about an overview of what I'm going to talk about, I will basically focus on this first part here. Reasons for increasing the number of heat pumps. What is the problem, what is the solution, and what are the obstacles? And then Michael will continue, and we'll see how far we get in this part. This is actually a shorter part, even though it looks longer on the slide here. So what is the problem? The problem is this. I don't know if you have seen this before, but this is the carbon dioxide concentration in the atmosphere during the last 450,000 years. And as you can see, the level has always been below 300 ppm. And even if you would go much further back in time, you would see that we have never had so high concentrations as we have now. And the increase is very, very rapid. This slide is from 2013. And you can see that only during these 11 years since then, the new red dot up here is a lot higher up than the end of the line here. So the CO2 concentration is increasing very rapidly. And this, of course, results in increasing temperatures in the world. So these are the temperatures during the last 2,000 years, more or less. And of course, we don't have data from the old times, no temperature measurements, but we can find out in other ways what the temperatures have been. And how do we know that we actually are behind this, that the human activities are the cause of this increase? Well, we have models nowadays which we can use to predict the temperature in the world, but depending on different factors. And with these programs, we can also see what would the temperature have been if we did not have emissions of carbon dioxide, for example, and other greenhouse gases. And as you can see here in the, let's see here, if we did not have carbon dioxide emissions and other emissions, we would have had more or less the same temperatures that we had in 1850. But this is not the case. So the models can show that the release which we have of CO2 is causing this increase in temperature. And the last year has actually been a very dramatic year. Here you can see the temperatures in July worldwide since 1940, and you can see that there is a drastic increase, and you can also see that in particular in 2023 the temperature increased quite a lot. And this is not the only thing. This is the sea temperatures, sea water temperatures. And down here you can see 4 different years since the measurement started, more or less. And then the red part here is the gap comparing the year 2023 to 24 compared to any other year before. So there has been a drastic increase in the sea temperatures during the last year, a little bit more than a year. And this is, of course, very disturbing. We don't really understand why this is happening either, and that is even more disturbing then. So this is showing the temperatures last year, and actually last year was the warmest year ever recorded with the thermometer, so to say. And just recently there was a release of an article in Nature stating that the temperature during 2023 was the highest in 2,000 years. And how can we know that? Well, one of the indicators we can look at are the tree rings, like you see on this picture to the right here. So if the weather has been hot, then the trees grow faster, and by that you can tell that the temperatures during the last 2,000 years has never been so warm as during last year. Yeah, and of course we can do some statistics on this, and temperatures go a little bit up and down, and the black curve here indicates the 5-year running average. So this lags behind compared to the red dots, which are the actual measurements of daily temperatures. And to the left you can see the scale here, so it's the number of degrees above the pre-industrial levels, let's say. So, and you can see that even now we are reaching some days already 2 degrees above pre-industrial levels. So yeah, I'll come back to this sort of the levels and what we would like to see, or what we hope to see. But the drastic increase during the last year is definitely something which we need to worry about. And this leads, of course, to different problems: heat waves, droughts, wildfires, and all of these are just headlines from different journals which I picked up from last year. And so many different things happened during the year of 2023, and this has continued into 2024 as well. And you have seen a lot of drastic changes due to this. The ice shelf around the North Pole is decreasing, resulting in the thawing of the permafrost, which is releasing more methane from the ground, for example. Yeah, you have seen ice bears before. This was from Germany, is it 1 or 2 years ago, when we had these floods. And so many different things you can see in the news actually showing this increase. But there are also some things which we perhaps do not talk so much about. And this photo shows migrants marching through Central America towards the US. And you could ask yourself, why are they marching towards the US? Of course, they want a better life. But if they could sustain themselves in a good way where they lived from the beginning, they would not have been moving. And I'm not saying that it's only because of climate change that they try to get to the US, but I would say that this is one of the reasons. And in the future, when some parts in the world will be more difficult to live in, difficult to sustain yourselves in those parts, people will start moving. And this will also cause social unrest, which is something which we do not talk a lot about. We talk about floods and wildfires and all of these things, but also the connection between global warming and social unrest is something I think we need to consider also for the future. So what is the solution? We have seen what is the problem. what is the solution? Well, we agreed, almost all countries in the world agreed in 2015 to try to stop the global warming. And this was done through the Paris Agreement. And what does that say? Well, the Paris Agreement says that we should try to limit the increase in global temperatures to less than 2 degrees, and preferably to 1.5 degrees. And this diagram then shows what would be the effect of continuing business as usual, continuing using fossil fuels in the same way we did before. And the green line is what is required if we want to reach the 2-degree scenario. And the blue line is what or curve is what we need to do if we want to reach the 1.5-degree scenario. And look now at the vertical axis here. It is the annual global total carbon emissions. So as you see, already in the middle of this century, we will have to have negative carbon dioxide, carbon emissions. And that is, I mean, this means that we really have to phase out all fossil fuels, and we also have to do something to absorb the carbon dioxide which is already in the atmosphere. And how we do that, well, that could be another lecture, but there is something called carbon capture. But it's a technology which is being developed, and yeah, it is not sure whether we can use it to any large extent yet, I would say. So what has different countries agreed on? Most countries have a goal when they would be carbon neutral. And as you see on this timeline here, most countries have aimed for 2050 as a year when they will be carbon neutral. Some countries will reach it a little bit before, and some countries have decided to try to reach it a little bit later. And of course, this depends on what conditions your country has. If you have a lot of, you're depending a lot of coal right now, you have a bigger problem. If you have a lot of, like Sweden, a lot of other natural resources which can be used, like hydropower and wind power, then it's an easier problem to solve. Yes, so will we reach our goals? One report which came recently from the United Nations raises some concern about this. It is perhaps not possible to reach the goals, at least not if we keep at the pace we are working right now. We need to do more. And actually in The Guardian just a couple of weeks ago, there was an article where they showed the result of interviews of a lot of people, a lot of researchers doing research on global warming. So each little square in the diagram here represents one person, and they should say, when do you think, what temperature do you think we will reach at the end of the century? So the goal, according to the Paris Agreement, is 1.5 or 2 degrees. But as you can see, almost all of the researchers thought that it would be more than 2.5 degrees or more. So 77% of the climate scientists expect a rise of at least 2.5 degrees. So even if we have the Paris Agreement, it seems unlikely that we will actually reach it. And of course, we should not give up just because of that. It's just to work harder. It's important to work harder. And if we don't reach 2.5, perhaps we reach 2.6 or 2.7. I mean, we must continue working on this. Yes. And in Europe, what we do in Europe? Well, we have decided to have a goal, but what does this goal include, so to say? So, von der Leyen has said that I want Europe to become the first climate-neutral continent in the world by 2050. And to make this happen, we must take bold steps together. And so several programs are launched. Green Deal is called, and one part of the Green Deal is what is called Fit for 55. And in this is not, 55 refers to the 55% greenhouse gas emission reduction by 2030. And just last year, these goals were also made a little bit tougher, so the improved energy efficiency was changed so that it should be 38% rather than just 32%, and 42.5% should be renewable energy sources, compared to 32 according to the old goal. So just to put things in perspective, let's look at the gross available energy in the European Union. 70% is actually still fossil. And you can see that the green part here, it's actually increasing, so renewables are increasing, but it's going at a relatively slow rate. And this diagram goes back to 1990. So if we should look ahead 25 years from now, that's something like half of this length to the right. And at that time, we should have phased out all the fossil fuels, and we should also be carbon neutral, or even carbon neutral by that time. So we have a huge task to do here to reach the goals which we have set for ourselves. So what is the strategy to reach these goals? I will talk about only one share of or an important share, but of the energy use, and that is the energy use in the European building sector. And looking into the statistics, we could say that about 40% of all energy in Europe is used in buildings. It's not only for heating or cooling, it's also for other purposes, but it's about 40%. And the energy use in buildings stands for approximately 37% of all greenhouse gas emissions. And I would say the most common way to heat buildings in Europe is to use gas heaters. And we have, according to different sources, it could be about 100 million or 130 million space heaters in stock. And a large share of these are old with relatively low efficiency. So if we want to, the lifetime of one of these heaters is about 25 years. So it would take 25 years to change all of these heaters to something more, something better. So you can see that the European building sector can contribute a lot to decreasing the carbon emissions. I need to talk a little bit also about biofuels, because one answer which is often given is that, well, we can burn biofuels instead. But biofuels, that's basically forest or materials from farming. And about the forests, of course, the best way to decrease the carbon dioxide emissions would be carbon dioxide levels would be to allow the trees to stay in the forest, right? Not to cut them to use them for firewood. So there is a lot of discussions within EU right now how to treat this, whether we should allow using firewood or not. And just to show you one diagram about this, the gray circle here represents the total energy use in the EU, and about 17% of this is renewables. And out of all of the renewables, including solar, wind, and biofuels, the bioenergy actually stands for almost 60%, which is much higher than I thought before I saw this article. And out of this 60%, about 75% is used for heating and cooling. So in several countries, firewood is still an important fuel for warming the houses. But we cannot expect to increase the harvest of biofuels. That's my belief. So it's questionable if you can harvest biofuels a lot, increase the harvest a lot. And when we talk about biofuels, we should differ also between wood and waste wood. Of course, if we cut trees for paper or timber, there will always be some residues, branches and roots, and we could burn those, use those as biofuels, but that's only a small share. And in the future, when we try to phase out the fossil fuels, of course, there will be much higher competition for the biofuels. So we can expect the price of biofuels to increase quite a lot compared to now. And we should also remember that biofuels is a good starting point for producing liquid fuels, for example, for aircrafts or for ships. So perhaps we should not use it just for anything. We should keep it for specific purposes as the resources are limited. So the reality then, in conclusion so far, is that the fossil fuels will be phased out. We have to phase them out. The biofuels will not be enough to cover up for the fossil fuels, which we don't dig up anymore. And the synthetic fuels like hydrogen produced from renewables, that's an inefficient way to heat buildings, at least. Could be used good for other purposes, for industrial purposes, for example, but for just heating it would be a very an inefficient way to use the electricity. And renewables and nuclear, well, what is the outcome of those sources? Well, it is of course electricity. So this means that we are moving towards an electric society. We are so used to having pipelines and for gas and for oil, but in the future we will have a lot of electric lines instead for transferring electricity. And we will use electricity for almost everything. We'll use it even to produce fuels sometimes, even though it will not be efficient, but we perhaps need fuels, or we can know that fuels can be stored, so for that reason we may keep it. So, and this is also the conclusion of the EU. So electrification is one of the pillars, so to say, on the that the European Union is basing its change of the future strategies on. And of course, electrification and heating, that means heat pumps. So extensive rollout of heat pumps is what is expected within the EU. And you can read this in the text coming from the EU. In the residential sector, the share of electricity in heating demand should grow to 40% by 2030 and to 50 or 70% by 2050. And in the service sector, the numbers should be even higher. So that's the expectations. And similarly, worldwide, if we look at IEA, that's International Energy Agency, they do prognosis about energy use or change of the energy system worldwide. And they say similarly then that the proportion of heating equipment sales accounted for by heat pumps nearly triples by 2030 and continues to grow thereafter. So heat pumps become leading heating and cooling technology in the buildings worldwide by 2040. And in another report just from September 2022, they state that we need about 600 million heat pumps by 2030. So it's an enormous amount of heat pumps which should be pushed out onto the market. And this just shows the trends up to now and how the trend needs to be changed in the sales of heat pumps to reach the goals which IEA thinks that we need to reach to be able to be sustainable. Then if we look at the sales of heat pumps, it's actually increased quite a lot. So this shows the sales in Europe from 2013 up to 2023. And as you can see, the growth is more or less exponential, even though something happened in 2022. And that was the winter when we had extremely high gas prices, extremely high electricity prices as well. But at that year, a lot of heat pumps were sold. So now we're sort of back to normal again. But the trend, the expectation is that this will increase. So the top of this graph is 3 million heat pumps here. And if you look at the expectations based on what has been stated from the EU, you can see that we need another scale. So to the left here you have 14 million heat pumps instead, and that is by 2030 or 2031. So you can look at different policy documents and you will see that there is a drastic increase in the number of heat pumps. And the numbers may be different in different sources, but it's something around these numbers which I show here. This was another source, also European Union. In this source they stated that we should be able to produce or sell 10 million heat pumps by 2027. So we were now at 2.5 million. So 4 times as much by 2027. And this is from the European Heat Pump Association, their expectation related to different countries. And as you can see, France is the country where they expect to sell most heat pumps will be sold. Germany is second, and then you have Italy and Poland and the rest of the countries in Europe here. But according to this, their expectations, then it should be possible to install 43 million heat pumps by 2030. So even more than what the European Union, so to say, prognosticized. The European Union is also working on a heat pump action plan. And this plan will then state some policies for facilitating the installation of heat pumps. This should have been taken before the EU elections, and it was unfortunately postponed, so we don't know exactly what will happen now, but it will probably be taken later this year with the new parliament in place. But there are some countries where they already took decisions. So in France, they have a national heat pump action plan, and they have a plan of producing 1 million heat pumps per year by 2027. So they have taken their decision already on this. So, of course, there is some resistance against installing heat pumps, and this is mainly for economic reasons. It's more expensive to buy a heat pump compared to buying a gas boiler. So the governments of Europe have introduced some measures to force homeowners to use heat pumps in the future rather than gas burners. So this map here shows which countries have bans on fossil fuel boilers, and it's difficult to read to the right there, but of course it depends between the countries. Sometimes it's from a specific date, and these dates can be different. Sometimes it covers both oil and gas heaters, sometimes it's only oil, etc., etc. But all of the colored countries here have some type of bans against fossil fuel boilers. And acting in the opposite direction then is that several countries also have subsidies for supporting the installation of heat pumps. So in the left you see the subsidies, the countries which have subsidies in new buildings, and to the right you see countries which have subsidies for renovations. And obviously almost all countries in Europe have some types of subsidies for introducing heat pumps. Now, if you look at the different countries, you will see that they are very differently mature in their use of heat pumps. So the different countries are seen on the left, starting with actually the Scandinavian countries, Norway, Finland, Sweden, Denmark are here, and then you can see all the other countries below. And what this graph shows, what is the likelihood that a house owner would buy a heat pump rather than another type of heating system? So in Scandinavia, it's more than 90% chance that the buyer will select the heat pump, while in the UK, it's only 3% chance that the buyer will buy a heat pump and not a gas heater. So it's a big difference here between the different countries. And this is also something which we should recognize. Of course, I talked about before the difference between heat pumps and gas heaters, and this shows then the difference in efficiency. So a heat pump has we call coefficient of performance. So this means that for each unit of electricity you get about 4 units of heat out. So the efficiency is then 400%, as you see here. While a gas heater, well, it could never be more than 100%, right? But it could be sometimes less. So according to the slide I showed before, there are many old heaters which have efficiencies of about 60%. So, and this influences, of course, the total use of energy. because if we use energy more efficiently, we can reduce the total amount. So this 70% fossil fuels will be reduced to a lower number, so to say, if you use electricity rather than fossil fuels. So it's the same as electric cars. We know that electric cars require less energy than the ordinary fuel or diesel cars. So finally, what are the obstacles? There are some problems on the way. And one problem is what we call F gases. So heat pumps and refrigeration equipment traditionally has used what used to be called safety gases, because they were not flammable and not poisonous. But they turned out to have bad effects on the environment. We have heard about the ozone layer, and it's also so that the newer refrigerants, they have high global warming potential, so we should try to get rid of them for that reason. So just before I talk about the different refrigerants, I just want to point out that there are, of course, different types of heat pumps. We have air-water heat pumps, the left column here, and they could be located outside or inside or be split units. Same thing we could have water-water heat pumps, well, either localized inside or split or only outside, or we can have air-to-air heat pumps. So, and these types of heat pumps, they are manufactured in different countries, and this has an effect on what type of refrigerants they are using. So here we can see that the most common types has traditionally been air-to-air. So it's like this split air conditioning units you probably have seen many times. The sales of those are decreasing, while the sales of air-to-water heat pumps are increasing. And the water-to-water heat pumps are decreasing a little bit. But these air-to-air heat pumps, they're almost exclusively built in Asia. And they very rarely use natural refrigerants. They use these old-fashioned synthetic fluids, which have some environmental effects. On the other hand, the air-water heat pumps, they are typically built in Europe, or there are many manufacturers of these, also water-water heat pumps. So here there is a larger chance that these will be using some natural fluid. So here we can see the distribution of different fluids. So R290, that's another name for propane. So that can be is an excellent refrigerant. R32 is a synthetic fluid which has a little bit lower greenhouse warming potential than the old one, R290. So R32 is increasing while R410A is decreasing. And then there are some others. But of course, I think both me and Michael here agrees that we should try to use natural fluids like propane in the future. And that's much of what our research is about. So this is coming from an informatory note, and it's an estimate of the heat pumps sold in Germany. So when you buy heat pumps, you have to apply for funding, and thereby, when you do that, you state what refrigerant your heat pump will have. So that's a way of trying to figure out how many heat pumps of different types are sold or with different refrigerants. And we can see then that the propane heat pumps are actually increasing in numbers quite a lot, and they reach now about 20%. And while 410A is going down, which is good, that's the old one. R32 is still increasing, but it's sort of a change from this 410A. So hopefully the propane heat pumps will increase a lot in the future. We have also international agreements trying to phase out the use of F gases or these synthetic fluids. So this is a diagram showing how much the GWP weighted maximum amount is in different parts of the world, according to what we call the Kigali Amendment to the Montreal Protocol. But in Europe, we also have new regulation from just a couple of months ago called the F-gas regulation. And according to this regulation, we should phase out all use of HFC, so the most common type of synthetic fluids. There is another type which is called HFOs, which will be allowed in this not included in this phase out. But also for these HFOs, the last remaining type of synthetic fluids, there will be restrictions. So small heat pumps, less than 12 kilowatt, small heating system or refrigeration systems will not be allowed to use HFOs either. So, yeah, there is another problem, and that is what is called PFAS. You probably heard about that in the news. There is Teflon, you probably know about, and that is one of the PFAS. There is a movie about when they found out that Teflon was actually not so good for the environment. Black Waters, I think it's called. It's interesting to see. Anyhow, so the PFAS have negative effects on people and on the environment. That does not mean that all PFAS has such effects, but just to be sure, there is a suggestion in Europe to phase out all PFAS. So this will have a large influence on the phase out of these refrigerants which are synthetic. So almost all of them are considered PFAS. So how will we handle the refrigerant problem? The synthetic refrigerants are strong greenhouse gases, and they belong to the PFAS group. And if they don't, they could also decompose into PFAS. And the phase out of F-gases decreases the available amount of synthetic refrigerants. And at the same time, we want to increase the amount of heat pumps exponentially, as I showed you before. So this is, you could say, a problem. We need to develop new heat pumps which can be run on natural fluids like propane. And the natural alternatives, they are flammable, and they could also be poisonous if you talk about ammonia. So this will need to be handled in some way. But we will have to learn to design safe systems with flammable refrigerants. That is my belief. And this is something we work on, both Michael and myself, since many years. So I think I will stop here and let you in here and talk more about the technical details.
Thank you very much, Björn. Tack ska du ha. Let's see. Working. Question to the audience: you want to keep in English, or you want to have it in German or in Danish? English is fine. Okay. So then I continue, and a little bit different from what Björn said. From me, you will not. You will also get some more details, but you will also get an introduction to what a heat pump is, because Sebastian told me that the majority of the students is electrical engineers, and you may not know what the heat pump is or how it functions. And this is just to support what Björn said. You can see here the buildings. They are responsible for about 15% of the greenhouse gases in Germany. And this is what the International Energy Agency says. They say that to the year 2040, which is not that far away, most of the savings come from either reducing the energy demand, so making the buildings more energy efficient, or changing electric heaters, resistant heaters to heat pumps. And the other part comes from renewable energies, and the heat pump actually is considered to be renewable energy. Let's look at the heating system. So here you have the total CO2 footprint. The numbers vary a little bit depending on whom you ask or which source you take. But you can see here for a typical German household, about 33% of the greenhouse gases, CO2 emissions, come from the heating and the hot water. Of course, it can vary a little bit. Yeah, if you have, like I had some years ago, one of our sons, he could take a shower every day for like 45 minutes. Then maybe the CO2 contribution from the hot water or the warm water is a little bit higher. Then you can have different heating systems or different systems to warm your hot water. Could be an oil burner or a gas burner, and the gray cloud shown there, the smoke, is an indicator of how much CO2 is released. And you can see there that, what is this down there, Holzscheit or pellet kessel, it's very small. The heat pump, it depends a lot on the COP over an entire year. We will have a quick look at that in the next 2 slides. If those numbers are correct, like 2.5 for an air source heat pump or 5 for a water source heat pump. And of course, with the heat pump, it depends a lot on where you get the electricity from. If you make the electricity yourself with PV panels, then it's completely CO2 neutral. Let's have a look at the coefficient of performance of a heat pump. This is an investigation from Fraunhofer ISE for existing buildings, and this is for a heat pump with air source. And on the previous slide, it said something of 2.4. If you look here at the bars, the light blue bars, they're all well above 2.4. So probably this assumption on the slide before has to be corrected a little bit to a higher value for the air source heat pump. And if you take water source heat pumps, there the value was something around 5. The green bars here, they're all below 5. So that value has to go down a little bit. Because there's a very bad or poor reputation for air source heat pumps, especially in Germany, and that people always say, oh, you have to drill a hole in the ground, you have to spend those 30,000 euro for getting the ground probes done. Bullshit. Yeah, you don't need that. You can just use an air source heat pump, especially in an area like here in Karlsruhe, where we hardly get any temperatures below 0 degrees during the winter time any longer. So put it here on this. Yeah, you can see the table for the air source heat pump. The CO2 emissions are probably lower than what is in this publication, but for the water source heat pumps, it's probably a little bit higher. Now, looking at the fundamentals for the heat pumps, you can see here that yeah, this is the way it works. So you take some energy from the ambient, you put in some electricity to drive the compressor, and then you can heat your house. And it's especially a renewable system if you get your electricity from either PV or wind or some other renewable power. Heat pumps are nothing new. This is the first description of a heat pump I found. It's from 1855 from a guy called Peter Ritter von Rittinger. And they used, or he installed heat pumps in paper mills. And then the first real heat pump patent I found is from 1912 from Switzerland. And this heat pump, the one from Switzerland, from this patent application, is very similar to what we have today. So this is a kind of a ground probe, but contrary to what we use today, where we have water glycol mixture here, he wanted to evaporate the refrigerant there. And this is something like the professor who was the supervisor for my PhD, he kind of invented this or reinvented this in the 1990s. You can see here, this was already in 1912 patented by someone, so to have the refrigerant going into the ground. And this is one of the really installed heat pumps, first ones. This is from the City Hall in Zurich in 1942. And another one 4 years earlier was 1938. If you think back of what happened at that time, 1938, 1942, this was World War II. There was a shortage in coal for Switzerland. They couldn't get it. So they installed a lot of heat pumps in that time period. We saw another boom for heat pumps in the 1970s when there was the oil crisis. We see like a third boom now, and hopefully now it's the breakthrough that the heat pump really will take over. Now, if you have been asking yourself throughout this presentation from Björn and from me how a heat pump works, it's just the opposite of a refrigerator. And this guy is asking himself, yeah, now I turned my refrigerator upside down, but it's still not working as a heat pump. So let's look how the heat pump functions. We do have an evaporator similar to what we have in the fridge. In the refrigerator, it's inside to cool your butter, milk, or beer. For the heat pump, it could be in the ground, as in this patent application from 1912 from Switzerland, or can be inside the heat pump, and then you supply some heat. In the air source heat pump, it would just be the outdoor air. The refrigerant is evaporating, and as Björn has mentioned several times, the best refrigerant for the heat pump nowadays would either be propane or could also be CO2 or ammonia, depending on the application. So we call this thing an evaporator, or Verdampfer in German. And the pressure inside this vessel depends on the temperature. And then, of course, we have to get rid of all the vapor. We use a compressor for that. This is electrically driven. Typically, in a heat pump, a hermetic compressor is used. And we discussed today when we walked through our lab, Björn and I, that the best compressor is one where it's just very compact, of course, and there are some nice developments from the automotive industry which could be used. Then we have to churn this vapor into liquid. This is done in the condenser, and this is where the heat pump is rejecting the heat to heat the house or the water. And then, of course, we have to connect this to make it a closed cycle, and we use an expansion valve for that. So these are the German names. So the evaporator, the compressor, condenser, and the expansion valve. And here you have the energies. This Q dot E is the heat we take from the environment. Then we put in some work into the compressor, and then we get the sum of those two for heating our building. And if this coefficient of performance is 4, it means that we get 4. This Q dot C is 4, and like 4 kilowatt heating with 1 kilowatt electricity, for example. So this is a little bit more advanced, and I think Björn, you had the same drawing in your presentation, or a very similar one. So this is how the heat pump works. And you can see you can use air as heat source, or the ground, or groundwater. This is how heat pumps look like. It could be like everything contained in one housing, placed outside, typically placed outside, because you do have the compressor, and the compressor makes a lot of noise, and you don't want to have that inside your house. A tip, if you want to install an air source heat pump, install it somewhere where the neighbor doesn't see it, because if the neighbor sees the heat pump, he thinks it's loud and noisy. If he doesn't see it, he will never notice that there is a heat pump. And then this is a monoblock system, or this is water to water. And these can be made very compact. Fraunhofer ISE, they have developed a system with 150 grams of propane. You have an idea, 150 grams of propane? A hairspray can, like a hairspray, the larger hairspray cans, like anyone is using. Like you have one in your bathroom probably, 150 grams. So how much propane is in the hairspray can? Or we can start with a lighter, the smokers among you. How much propane, butane mixture is in a lighter?
1 gram.
A little bit more, about 2.3. In the hairspray can, you have 180 gram propane. And at Fraunhofer ISE in Freiburg, they managed to build a heat pump, 12 kilowatt heating capacity with 150 gram. So this is less than what you have in a hairspray can. And there are no restrictions where you place your hairspray can. You can have it in the bathroom, you can have it in the kitchen or in the basement, but with the heat pump, there's a lot of discussion if it's safe to use a propane heat pump. Now for the refrigerants, these were the refrigerants in the very early days, all natural fluids, because there was no chemical industry. Then we got the CFCs, and they were used for virtually everything. Like when I tell my students that we used to clean the condenser of a refrigeration system with refrigerant from the refrigerant can, they're all like, oh, how could you do this? I mean, everybody was doing it because all the spray cans, hairspray, deodorant, everything used CFCs as a propellant. So this was normal until the 1970s. And actually the US was the first country in the world to say that you could not use CFCs anymore in spray cans. In 1976. So those synthetic refrigerants, they brought us the ozone hole, they brought us global warming, and now the new fluids, HFOs, they even bring us to destroy all the water, the fresh water sources we have. So it's here you can see that refrigerants, they conquered the world from the stratosphere to the soil, to the ground, and this is for sure not sustainable. And here just 2 slides, I think, on this HFO thing. Because these new fluids, they are designed to break down in the atmosphere very quickly, and they form something called trifluoridic acid. And this TFA may have an influence on the fertility of animals and thereby also on humans. And there's an increasing amount of TFA in all the freshwater sources coming from the refrigerants. And you can see here, this is a comparison from the 1990s, 1995 to today. It's a factor of 3 to 5 higher. In the Rhine River, the Rhine River is very close by. You can see here how the concentration is increasing in the Rhine River, from 0.4 microgram to 1.4 microgram in Düsseldorf when it exits Germany. This is a simulation from British scientists. They say all the 134A, the old HFC refrigerant, emitted to the atmosphere today, converted into or replaced by this HFO fluid 1234YF and emitted at the same location. The difference is 134A only has 20% TFA formed in the atmosphere. This 1234A YF forms 100% TFA, so it's 5 times more. The other difference is that 134A has an atmospheric lifetime of 8 years, so whatever you blow into the atmosphere here in Karlsruhe will break down in South Africa, in Australia, in Antarctica, somewhere on the globe, but not here, because it's first in 8 years. 1234YF breaks down within 2 days. So if there's a day without wind, whatever you emit here from a car air conditioner will break down right here. Or Stuttgart is even worse because you have this valley and there are 800,000 cars in Stuttgart and they all emit this 1234YF. That's why we get this yellow and orange spot right in our area here. So the prediction is that we give 250 times higher TFA concentration. 250 times more. And all this will end up in Lake Constance, Bodensee, or in any other thing. And Lake Constance, the water from Lake Constance is used as drinking water in Stuttgart. And there will be in a couple of years that they cannot drink it anymore. Very nice. Because of that, there's this proposal from 5 European countries to the EU to outlaw not only TFA, but all different kinds of PFAS, all these forever chemicals. And there's a similar announcement from California, and there are also things going on even in China on this topic. So we will see what happens. This is my own personal view on those HFO refrigerants. I mean, some of you may need a pocket calculator for calculating this, but this is the wrong way. I mean, it's the wrong way to use a pocket calculator for an easy thing like this, but our daughter does. But the other thing is, this is not a calculation. What I mean with this is, it took 60 years to figure out that the CFCs damage the ozone layer, and then the replacement fluids, the HFCs, they contribute to global warming, and that took 30 years. And I say that it will take about 15 years to get rid of the HFOs again. And the first time I showed this slide is now 7 years ago, so there are maximum 8 years left for the companies manufacturing these chemicals. Luckily, there are alternatives. We can have CO2, we can have ammonia, we can have propane, or isobutane as you have in your refrigerator at home. There you can actually check. There are small nameplates where you can see what the charge is, how much isobutane is in your refrigerator. Any idea how much it is approximately? So we said 2.3 gram in a lighter, 180 gram in the hairspray can, so in the fridge. Small fridge, 25, 30 grams. The larger ones maybe 70, 80 grams. And the limit is at 150 because they 30 years ago said the typical kitchen has this size, and the maximum isobutane level you want in your kitchen is 8 grams per cubic meter, and then they came up with 150 grams. So if you have a smaller kitchen and you leak the refrigerant, you may have a problem. And if you have a larger one, then you never have a problem. And of course, you can also use water as a refrigerant. Perfectly well. I will show you an example from Denmark on a heat pump running on water. This is a heat pump running on CO2, and we have a similar system in our lab. So all the students from mechanical engineering or mechatronics, they test, they can try this equipment. This installation was at a Mensa in Soest, in the University of Applied Science. And you can see there the bottom line is payback, return on investment, payback time, 1.8 years. So it's actually very beneficial to use a heat pump. And the nice thing with CO2 is that you operate it in a so-called transcritical cycle. So in the pH diagram, here's the critical point, and then you are above the critical point, and you have a lot of energy you can take out of the CO2. That's why CO2 is very good for heating water. Actually, the largest CO2 heat pump in the world is right now installed in Esbjerg in Denmark. It will supply the entire district heating system with heat from the North Sea. So they take the water from the North Sea and then pump it up with the CO2 heat pump to supply all the houses in Esbjerg with heat. And if you're interested in that, you can listen to the presentation on the 7th of November. There will be someone coming from Norway who is kind of on the project team. They will present this heat pump at our Energy for You. This is another heat pump you will be able to see at this Energy for You, or you could see it tomorrow during our heat pump symposium. This was invented by 2 students, mechanical engineering students. They came to me one day and they said, "Oh, Michael, we had the crazy idea yesterday when drinking beer." And I said, "Oh, what idea was it?" And they said, "Oh, we want to build a Weisswurst Wärmepumpe, a sausage heat pump." I said, "Okay, what is a sausage heat pump?" And he said, "Oh, you have to heat the sausages and you have to cool the beer. So we take the heat from the beer and put it into the sausages." And I said, "This is not a crazy idea, it's a brilliant idea. Go ahead and build this thing." So they built this thing, and then they made some measurements. You can see there, it takes about 45 minutes to cool 30 bottles of beer and to heat 80 sausages. And what they found out when they made this self-test is at a certain point, the average student is no longer hungry, but still thirsty. So they put in an air-cooled condenser. So this thing can always cool beer, but doesn't have to heat sausages. And it's a nice thing. We used that. We were last week in Frankfurt at the Achima with this thing. And you can see down there, you have 385 grams of isobutane. So it's well below the 500 gram limit, which is now for commercial applications. And the nice thing is you can only do this with isobutane. We have an evaporation temperature of -2 and condensation temperature of +95. It's not possible with any other refrigerant in a single stage process. And this was when they had their final presentation. Of course, they got the highest grade. Then you could say, okay, isobutane is flammable. What about that? There were some tests done on air source heat pumps if they leak, and you can see there. There's a little flame, but it will not blow up the house, and it will never kill any people. And there's this at the bottom line there. It says a study from Switzerland from 1999. It's 100 times less risky than having a gas furnace. And a gas furnace is well accepted. This is this Swiss study from 1999. And you can see here on the left-hand side, it's how many dead people you have per year and how many injured people you have per year. And it's a little bit, of course, for the guy installing everything, but for the homeowner, nothing. And here, the scale here, the scale on the left side and the scale on the right side is different. So you have the homeowner, and then the homeowner with the gas furnace, and driving with a car. So it's perfectly safe to have propane in the heat pump. If you do have some doubts, then you could go to water. It's the perfect refrigerant because it's not flammable, it's not poisonous. But if you look on a worldwide basis, there are more people dying because of water in their lungs than people dying with ammonia in their lungs or with a house exploding due to propane. So actually, water can also be very dangerous. And there are some companies listed there who are working with water as refrigerant. And the one I want to show you is this one. It's my former colleagues. I used to work in Denmark. It's also why I can speak Danish, unfortunately not fluent Swedish, but we can get along. And tonight when we will sit in the restaurant and after the third beer, then Björn and I can talk a fellow Scandinavian language. This is a heat pump installed in Aarhus, also for district heating system. They use water as refrigerant, and also the heat source is water. They use the water from the harbor, and the first stage is a water vapor compression heat pump, and the second stage is an ammonia heat pump. And you can go there, it's like an open museum. If you ever make it to Denmark and to Aarhus, go down to the harbor. It says on the outside, Maskinhuset. You can go inside and have a look and see how the system is working. And there you see the gray part is the water heat pump, and the green part is the ammonia. Now, just a few ones, but maybe Björn, because I think you have in your presentation nicer pictures and better explanations. This is an air source heat pump, which you probably have seen. And this is, if you look there, this is the way some of them look like. You shouldn't do that if you have a neighbor here, because then that neighbor will say that this thing is noisy. But if you place it somewhere where he cannot see it, then it's fine. This is ground source heat pump, like this patent from 1912. He had the refrigerant in the ground. Typically, you have in the ground a water glycol mixture in Germany. In Sweden, it's water ethanol, because the water ethanol is better from a thermodynamic point of view. But of course, some people drink the water ethanol, even though it's denaturated. And that was a case. Åke Melinda told me once they had a case in Sweden in a hospital with this ground source heat pump running on water ethanol, that they had a leak and they couldn't find the leak until they figured out that there was a small tap for taking a sample, and this tap for taking the sample was in the department for the alcoholics, and they were actually drinking it. And this is the typical ground source heat pump where you have ground probes in the earth, and we had here at our university a nice project some years ago. We developed a measuring system. It's a very small ball or sphere which can float through this ground probe and take the exact temperature distribution throughout the ground. This is something you can also do. It's like you have one central heat pump making the first step, and then you distribute the heat in a ground network, but at a temperature of maybe 15 to 20 degrees, not 70 like a district heating system. So the heat losses in the ground are smaller, and then in each individual house you have a small heat pump. The way they do this in Fischerbach and in Bleichach is with an ice storage, seasonal ice storage, and they freeze the ice, it's called ice on coil. So they have some plastic piping inside a very big vessel filled with water. The plastic pipes run a water glycol mixture inside, and this water glycol mixture is then going to the heat pump, to the evaporator, as the heat source for the heat pump. So you have several like heat exchangers. The efficiency is not very good, and we had a European project until last year, 2 years ago, with I think something like 10 partners, where we improved this system. We removed all the plastic pipes in the storage vessel and just had the evaporator of the heat pump itself produce supercooled water. You may have experienced supercooled water yourself. Take a plastic bottle, place it in the freezer, and cool it down to -4, -6, and it's not frozen. And then you open the lid, and the CO2 initiates the freezing process, the crystallization process. That's exactly what we did in this European project. So we cooled the water down below the freezing point, and then afterwards we had the crystallization. We could increase the evaporation temperature by 10 degrees. And 10 degrees increase in evaporation temperature means 20 to 30% energy increase as compared to this system. Last type which I will present is this one. You can of course also use the exhaust air from your building, for example, to heat hot water in a heat pump. And then, oh, I'm sorry, there was one more. This is a groundwater water heat pump, so you can take water from the ground and pump it back. That's what they do here in Karlsruhe at the hospital. And in Rapperswil and at the Lake of Zurich, where I live, they use it for the zoo, for the elephants, to heat the elephant house. And then in the future, and this is something Sebastian and I have talked a lot about, are these PVT collectors. This is a PV collector making the solar energy into electricity, at the same time also producing heat. So you get the electricity to run your heat pump, and you can take the heat from those PVT collectors as a heat source for the heat pump. And then those systems are very efficient. And there is at least one company already doing this in Switzerland, in Zurich. But maybe we can still make a research project out of this, and maybe Björn, you have it in Sweden as well, even though the sun is not shining that much in Sweden as compared to here. And then the other source, energy source you can use for heat pumps is all the heat from the refrigeration systems. When you drive here from the university towards Entenfang, you have this like commercial area. There's a large tire manufacturing, like a plant from a French tire manufacturer. They have to cool all their equipment, so they have a refrigeration system which has something like 1.5 megawatt refrigeration capacity. Now the coefficient of performance of that system is not 5, it's maybe more or less like 3, but that means that they blow some 2 megawatt of heat into the air in Karlsruhe. And at the same time, there are 39 other companies surrounding. They all need some heating. And the easiest thing you could do is just put a heat pump on top of this refrigeration system. And Andrea, we had this some years ago as a study. I don't know what happened if they installed it, but I know that they did in Waldbronn. There's an ice skating arena. Very nice design. Ammonia as refrigerant. Next to it is an open-air swimming pool. And they said, okay, we take all the heat from the ammonia system and put it into the swimming pool. The little thing they forgot is that the swimming pool is open from May to September and the ice skating rink from October to March. I was there once with students in January, and it was the pool was packed, but not with people, with birds. They had 25 degrees warm water, and there was snow surrounding them. And then I said, I mean, how stupid can you be? On the other side of the street, there are a lot of companies. Just get a pipe from here to there and heat all those buildings. And that's what they're doing now. So this was installed. So this is the conclusion. Heat pumps are the heating system for the future, what Björn also tried to tell you. And I think we still have maybe quickly go through your slides or the last ones. In case you want to know something about natural refrigerants, there's a nice book about natural refrigerants. And there's tomorrow afternoon a whole conference on heat pumps. In Steinway's building, unfortunately, all the seats are taken. There's no more space for coming there live, but you can follow on YouTube. If you go on our homepage, the Hochschule Karlsruhe homepage, there's the link for the two YouTube things. Björn will also present again. I will present something. And then the other thing where you can go live, if you are fast enough with the registration, is the 7th of November, this Energy for You, where we also will have a lot of things on heat pumps. And in case you as the students, if you are in Karlsruhe in September, we have 1 week sustainability summer school. You will get free ECTS, free credit points. It's a full week program starting Monday morning at 8 and finishing Friday evening at 6 or 7. It's only €100 to participate. We have space for 40 students. We will have a lot of interesting exercises and excursions, technical visits, and we will also have a lot of fun. So, now you? More questions?
Should we take some questions?
I think we still have half an hour.
Ah, half an hour.
I mean, if you have questions for half an hour, we can stop here, or otherwise Björn can take 10 minutes more.
Okay. Yeah, give me 10 minutes then. Thank you. So, as you may notice, there will be some overlap in between the presentations, but I hope you don't mind. So we talked about different types of heat pumps. You have some more slides about that. And I can add some things. I mean, it is sometimes claimed that energy, or we should use electricity in some other way than for heating. That was the old way of thinking, I would say. But now, as all the energy will be supplied in the form of electricity, we will definitely be using electricity also for heating. But one problem with renewables is, of course, that it's not a steady source of energy. So sometimes it's windy, sometimes it's sunny, sometimes it's neither windy or sunny, and the price of electricity will go up and down. And our response to this then is that to say that heat pumps can actually be used to even out these variations in availability in electricity and the electricity price. Nowadays, everything is connected anyhow and controlled in different ways. So it would be relatively easy, and that is already done in some places, to control the heat pump so that you run them as much as you can when it's when the electricity is cheap, and when it's the electricity is expensive, you avoid running it. So this is just showing some graphs of availability of the energy price and the availability of energy, and how you could, so to say, shift the loads from hours of high peaks to hours of low peaks. And this could be done with a heat pump then, where you also include a storage. So even though the house is warm, you can still run the heat pump, and in this case it's phase change material here, so you basically allow a wax to melt during the nighttime, for example, when electricity is at low cost. So that is one way to use the heat pumps as a part of an intelligent energy system. We already talked about decreasing the charge, and this is some examples from our lab. We also did a heat pump with isobutane, working with 120 grams and 12 kilowatt in capacity. So it's comparable to what they now have done also in Fraunhofer. And yeah, there is a lot of interesting development here, both on the compressor side and on the heat exchanger side to reach this, because previously it has not been important to have low charges, because the refrigerants were not considered to be dangerous in any way. They were not flammable, not poisonous. So there was no pressure to try to decrease the charge. But nowadays, because of the flammability, and also I would say because of the effects on the environment, we try to reduce the charge. And this has had a big effect. If you compare different heat pumps, you will see that some use a large charge for a small capacity, and others use a small charge for a large capacity. Yeah, so how will we solve this problem with the gas heaters? Is this what we will see in the future? That could be a question, right? I don't think anyone would like to see cities like this. And there is research going on this also. How should we manage this? And this is just a picture taken from the LCR 290 project, which they're running in Fraunhofer. And you can see that there are different options here. You could have sort of one heat pump for each level, or you could have one heat pump in the basement and then have water sent around in the building. or you could place a heat pump outside and then heat the building. And of course, another solution would be to have district heating. And district heating is not an energy source, as some people seem to believe. And district heating is a way to transfer energy, right? So you still need some way to heat the water in the district heating pipes, and that should of course be heat pumps. So just to continue, this is University of Stockholm, where we're using heat pumps, and we were involved in the project where we made a large number of boreholes, 130 boreholes, 230 meters deep. So these boreholes can be used for dumping heat during the summer when it's hot, and for extracting heat during the winter when it's cold. So the ground is sort of an energy storage in this way. And another slide showing a similar solution. This is a place where there is lots of gravel in the ground, gravel with water. So basically we have two wells, one cold well and one hot well, and during the summer we can dump the heat in the one side, and then during the winter time we can sort of say force the water the other way. But you would still need, of course, a heat pump here to allow this to work, because the temperatures down, or the water down here is far from the temperatures we need for heating. What else was there? Yeah, so, I mean, heat pumps will be used in a lot of different applications. You may not be aware of it, but electric cars need to be heated, and there is no waste heat from the engine there, so they actually have a heat pump already now. Both a reversible heat pump, which can be used for both heating in the winter and for cooling in the summer. And when you buy a new dishwasher or a new tumble dryer, you have the option to buy a unit including a heat pump. So heat pumps are there already in some products, and I'm sure that we will see more of this in the future. Finally, something on district heating. This is showing the energy input for district heating in Stockholm from 1970 to 2017. So back in 1970 we used almost entirely oil, and then you can see how the biofuels have taken over more and more. So there is very little fossil fuels now in the district heating production. And you can see also that on the top here, the green and the purple on the top, that's actually waste heat from this city waste, and also heat from heat pumps. And of course this can be, as Michael also said, used to a much larger extent in the future, because I don't think it will be possible to use so much biofuels in the future. Biofuels will be so expensive that we cannot use it just for district heating. That's my belief. This was just a picture showing what the heat pump looks like in that case. And Stockholm is a city of water, so there is a lot of water to take heat from. So here you can see another heat pump which is located on a pier here, and the water is taken from the center of this bay, and in the winter the water is taken from the bottom, and the temperature is about 4 degrees, and in the summer the water is taken from the surface, closer to the surface, where the temperature could be up to 20 degrees. And yeah, so it's a lot of water, of course, needed if you just have 4 degrees to sort of decrease the temperature during the winter time. So standing at this pier, it looks like standing at the back of a big ship. There's a lot of water coming out from the heat pump there. Yeah, I just want to mention that it's not only I who think that, or Michael who think it's important with heat pumps for district heating. IEA also has included in their report, The Future of Heat Pumps, some text on this. The decarbonization potential of district heating is largely untapped at present, with fossil fuels still supplying around 90% of district heating globally. So Stockholm is an exception here. You saw it, we used to use a lot of biofuels, but in other countries it's mainly fossil. So between 2030 and 2040, Denmark is set to provide nearly a third of the district heat supply with heat pumps. 4 European countries, Austria, Denmark, Finland, and Sweden, currently have targets to decarbonize their district heating networks to 2030. So that is the goal of these countries. And when we talk about district heating, traditionally this is like water of temperatures of 80 degrees or so, or perhaps 100 degrees, or even 120 degrees. But you could also build other types of smart grids where the temperature in the circulating water is much cooler, so cool that it could be used both for heating and cooling. And this is what is shown in this sketch here, which is actually an installation in Switzerland. So in some buildings they need heating, and then they use the loop here as a heat source. And in some buildings they need cooling, and then they use the loop to dump the heat. And of course, in each of the buildings they need either a refrigeration system or a heat pump, or both, or a combination. So, and this is discussed a lot. It's sometimes called 5th generation district heating. But with 5th generation district heating, you will have so low temperatures that you will need a heat pump in each building. That is one conclusion. And just to explain this in a little bit more, I mean, of course, this loop during the winter time will tend to cool down when everyone needs heating. So then the loop is connected to boreholes in the ground, which is basically used as a heat storage. So during the summer, the warm water, which is coming from the air conditioning of all the buildings, cooling of the buildings, will be pumped down in these boreholes. And then during the winter, the water is pumped the other way, or the heated up ground will be used as a heat source. So, and there are other installations. This is from Sweden. It's a similar type of installation. So, just finally, something about industrial heating. It is actually also possible to use heat pumps for higher temperatures. We didn't talk about how to calculate the efficiency of a heat pump, but basically it's very important to have as low temperature differences as possible. And I think Michael told you that in one of the slides when we talked about this redoing the ice machine. But so if you want to reach, let's say, 300 degrees or so, the efficiency would be rather low. But 150 degrees would be possible, and perhaps even 200. And if you compare it to direct electric heating, it will always be a bit more efficient. But the higher temperatures you try to reach, if you have a low temperature source, then the efficiency will be going down. But there are this type of machines already available. So here you can see on the horizontal axis you have heating capacity. So it's and this is basically different manufacturers or compressor manufacturers. And on the vertical axis you can see the temperature levels which can be reached. So there are already products being able to produce hot water at 150 degrees or 160 degrees even for. So it can be used. Heat pumps can be used also for industrial applications where you need higher temperatures than is usually needed for heating of buildings. So that was basically my last slide, but my conclusions, once again, global warming requires phase out of fossil fuels. I think most of us agree to that. Renewable energy and nuclear energy produce electricity. So heating will in the future be based on electricity. And according to political decisions, the number of heat pumps in Europe will increase. And this factor 6 or 7 different sources tells us different, but there will be a almost exponential increase. That I'm sure about that. Heat pumps will be used wherever heating is needed, from home appliances to district heating and industry. So I think that was, the larger increase and the simultaneous phase out of F-gas will require a transition to natural and flammable refrigerants. So with that, I think, thank you for your attention. I'll leave this up.
Thank you very much, Björn. Very interesting. We will learn tomorrow. There are some more presentations from Scandinavia. There's a Swedish heat pump manufacturer. They will present. And then we will also look at what the difference is, why heat pumps are so popular in the Scandinavian countries as compared to Germany. And it can't be the temperature, because it's colder in Norway and in Sweden. So it's should be even more attractive to do it in Germany. But maybe they have better politicians in Scandinavia. Okay, questions?
Okay. Thank you very much to both of you. Yeah, and now we have time for questions.
Ihr könnt auch gerne auf Deutsch fragen, ja? Kein Problem.
So you were presenting that they use the water from the harbor to, for the heat pump. What effects does it have for the environment when you put in the cold water or the warm water back into the harbor?
As far as I know, we have seen no effects. I mean, compared to the amount of water passing through this bay, the amount which is well, the temperature change of the water in general is so small that it doesn't have an effect. So,
if you heat enough buildings with the heat pumps, you may be able to get the penguins in in the scarecrow.
Yeah, yeah. We have a similar case actually with a nuclear power plant some 150 kilometers north of Stockholm, where all the cooling water is into a bay, and there you have a definite increase in the temperature. So some of the birds, they love this place because of the high warm water. But that is made on purpose, so to say. Just, yeah.
How do you see the future relevance of the PVT technology?
Well, I think they have a bright future. We just have to work on the manufacturing to make them cheaper, because the pure PV element you get from China nowadays is very cheap. And these PVT elements, they're manufactured somewhere in Europe, and right now the price is a lot higher than for a normal PV module. So we have to work on bringing that down, and also look at what is used as the heat transfer medium. Should it be air, or should it be water, or water glycol mixture, or should it be refrigerant, maybe evaporate refrigerant? And then next question is how do you set it up? Like if you do it with water glycol, then you have some connections which you have to make on the roof, which should be tight for decades. So yeah, there's still some development there. But it's the good thing is like the PV element is more efficient the lower the temperature. So if you actively cool it from down below, and with a heat pump you could cool it below the ambient temperature, then you get the high efficiency of your
Thank you.
Other questions? Maybe I can add one from the live chat we have from the internet. There is a question about a new or alternative technology for heat pump, the electrocaloric way. If I got that right, Rainer, electrocaloric heat pumps, where you don't need any refrigerants?
What does it say?
Yeah. I mean, of course, there are different other cycles which can be used for heat pumping. I guess is what. Yeah.
Yeah. Electrocaloric. Yeah. So alternative fluids, or we call it in the UNEP RTOC, we call it not-in-kind technology. I actually gave a presentation on that in September last year. And we have a colleague at KIT Campus North. Her PhD thesis was on that, and she has a whole group working on that. And she also participated in this presentation last year in September. And there are some nice technologies, but the conclusion is, like right now, they're all not competitive with the vapor compression cycle. This doesn't mean that they will never be, because if you just look at your watch. I don't know if there's anyone in the room who still has a mechanical watch. Most of them work with quartz technology. The same with the light bulbs. If you think just 20 years back, it was all Edison light bulbs. Nowadays, everything is LED. Maybe, I don't know, maybe we will see something similar in heat pump technology. But right now, it's not on the horizon. There are some things which are worked on like the research stage, but there's nothing which is able to be put into a house anywhere.
I could add to that. I mean, we had a PhD student who actually worked for Electrolux. They manufacture refrigerators, right? So they wanted to know if this was magnetocaloric was a good solution for the future, because there was a lot of discussions about this, a lot of hope. That's about 5, 6, 7 years ago. And I mean, our investigations showed that it was, we were very far from getting the same efficiencies as we would get with our ordinary vapor compression cycles. And I think there is one reason which is common to all of these alternative cycles. When you have a vapor compression cycle, the temperature change is in the fluid itself. You compress it and then the temperature increases, and then you can allow this fluid to give its heat to the ambient or to heat exchanger. But if you have these other cycles, and you usually have a material which heats up, and then you have to transfer the heat from this heated up material to some other place where you should then dispose it. So all of them have this problem that compared to the vapor compression cycle where the fluid itself changes temperature, you have to have another fluid which should be heated up and cooled down and transferred to another place and give off heat. So I think that is one reason why it's difficult to find alternative cycles. But it comes down to materials technology, I would say. We need better materials which change more in temperature when you apply the electric field or magnetic field or force, tension on these materials. And so it's not a mechanical engineering problem anymore. It's a material technology problem.
Like when I studied mechanical engineering at the University of Hanover in the north part of Germany, and had my thermodynamics lecture with a person called Professor Beer, Hans-Dieter Beer, and that was in 1985. And he said, because also in Hanover you could choose different subjects, and one of the subjects was, of course, refrigeration, and the other ones was design engineer and then production engineer. And this Professor Beer in 1985 said, you can choose any specialization within mechanical engineering you want, but don't choose refrigeration. Everything is invented, everything is known, there's nothing new. But what he forgot was the ozone crisis, ozone hole, global warming. Yeah, and I can tell you that like, I started working with refrigeration outside the university in 1986 when I went for a year as a guest scientist to the US to work at the National Institute of Standards and Technology. So I have almost 40 years of experience, and it has never been boring, and there have always been new things. So this professor, thermodynamics professor, was completely wrong when he said that everything is invented and nothing is new.
Yeah, just to add one more comment to that. They say that Einstein, when he wanted to relax, he invited his friends, and then they tried to invent a new cycle for producing cooling. So that was something they did in the Saturdays and Sundays, perhaps. New cooling cycles.
Okay. Maybe one last question from my point of view. Is there any reason, or let's talk about in the future, is there any reason that a heat pump, or in terms of talking about the costs that I have to pay for a heat pump. Nowadays, the costs are, especially in Germany, quite high, because I think about to the subsidies we get. Is there any reason that a heat pump is more expensive than a gas boiler? Or how much in terms of factor? Can you propose something? Right now, what is it? Three. Yeah, but it's 3-5 times higher price than for a gas boiler. 3 to 5 times more than a gas boiler. I think it is a little bit more complex. Yeah, you have to have a compressor and a fluid. It's easier to have just to get a gas from out of somewhere and to boil it, to burn it. But what do you think?
I mean, one of the reasons is the number of units manufactured and how automated they have everything. And you can get, I mean, the typical heat pump capacity for a single family house is, yeah, if it's an existing house, maybe 12, 14 kilowatt heating capacity. If it's a new built house, then you can get away with 4 or 5 kilowatt. Because they're better insulated. And a heat pump like that, I didn't check the prices now, but what was that, 10 years ago I checked, because I tried to replace my oil burner with a heat pump, and the two challenges were the same what you say with the price. I could get a gas furnace fully installed, everything for was almost around 14,000, like taking the old oil out and doing something on the hydronic system, and then putting this gas furnace in was 14,000. Then I tried to get some offer on a heat pump, which I couldn't get because they all refused. They said, no, this is an old building and we will not do it, and your oil furnace has 50 kilowatt. You need a heat pump at least with 25 kilowatt. And I said, no, I don't. I made some insulation. 12 or 14 kilowatt is enough. But if I had ordered a heat pump, a heat pump manufactured in Germany at that time, as a private person ordered somewhere on the internet, I would have had to pay something like 11,000, 12,000 euro. And as I said, I didn't get any heating company to make an offer on the heat pump, because they all thought that it's not possible on an existing house, which is stupid. It's not true. Yeah, you can place a heat pump in an existing house. You could even do it with 25 kilowatt. The top of the line was someone who said, okay, you can get your heat pump, but you need one with a ground source. And then I got an offer for the ground source, for drilling holes in the ground and putting these probes in there, 25,000 euro back then. Nowadays it's probably 50,000. And the very stupid thing from this company was like, okay, you have to pay those 25,000, but whatever we hit in the ground is your own mistake. You have to repair it. And I said, forget it, because this house has been here for 50 years. I don't know what is in the ground and where there are the cables and where there are the drainage pipes. And if you damage anything, then it's another couple of thousand euro. So I ended up ordering this gas furnace for 14,000. And when this person came, he was like, oh, you're Michael Kauffeld, you're working with heat pumps. Why didn't you order a heat pump? And I said, yes, I wanted, but no one offered it. Oh, we could do it. And I said, okay, now it's too late. I already paid for the gas to come in, so we will not do it. So this house has a gas furnace now.
Okay. Yeah. Just to add to that, I mean, I totally agree that it's a matter of scale. I mean, if you go out and buy an air conditioning system, a small air conditioning system split, it doesn't cost very much. And I mean, these are produced in many, many millions in Asia, right? So when we start producing the type of heat pumps we need in Europe at the same numbers, then the prices will be go down quite a lot, I would say.
The typical split air conditioning system is anywhere between 1,500 and 2,500 euro. And you can also get them now with propane as refrigerant, but not from European manufacturers yet, but from Chinese and Indian manufacturers.
Okay, thank you very much. Thank you to the audience for the discussion. And yeah, enjoy the afternoon, the evening. See you next week. Bye-bye.